Welcome to the Explainer. Today, we're diving into a seriously high-stakes architectural choice. This is something that sits at the very foundation of modern system design. We're going to do a deep dive into the trade-offs between the historically dominant relational data model and the massively popular modern document model. And to really grasp why this is such a big deal, we kind of need to look at how we got here in the first place. You see, since the 1970s, the relational model, tables, rows, columns, it absolutely ruled the data world. It was perfectly designed for an era when data was super structured and storage was incredibly expensive. But skip ahead to the 2010s, and the landscape had just completely shifted. The NoSQL movement exploded, we had a massive surge in web-scale data, a huge need for high concurrency, and developers were using agile methods where they needed to iterate fast without waiting around for database admins to do painful migrations. So the document model became the poster child of this whole movement, storing data as these continuous, self-contained JSON or BSON documents. Ultimately, choosing between these two paradigms is literally one of the most consequential decisions your engineering team is going to make, purely because it dictates how efficiently and securely your app interacts with its data. So the big question we're tackling today is relational or document? And I want to pose this directly to you right now. As we go through this explainer, I really want you to just drop any tech tribalism. We see it all the time in the developer community, but try not to frame this as a battle of good versus bad or legacy versus modern. Instead, look at this purely as an engineering search for the right tool for the right job. Neither of these models is a magic silver bullet, and honestly, neither is perfect for every single use case. As we're going to see, the inherent structure of your application's data, along with your read and write patterns, that is what should dictate the model you choose, not just whatever framework is trending on Hacker News this week. All right, let's start by looking at why the document model gained so much traction to begin with. It basically comes down to solving a massive developer headache known as the Object-Relational Impedance Mismatch. Think about how we actually write software today. The vast majority of our code is object-oriented. And in an object-oriented world, our data is represented as these rich, nested objects full of lists, maps, arrays, you name it. But traditional relational databases, they don't understand rich objects. They only understand flat tables with rigid rows and columns. So bridging that gap between your beautiful nested objects and those flat tables requires this incredibly awkward translation layer. Historically, developers had to write thousands of lines of boilerplate code just to pack and unpack this data. Now, today, we usually use ORMs, Object Relational Mapping Frameworks like Hibernate or Entity Framework, to hide that boilerplate. But any experienced developer will tell you that ORMs leak their abstractions all the time. They generate wildly inefficient SQL, they get hit with the infamous N+1 query problem, and they burn through CPU cycles just hydrating flat rows back into objects. The document model promised a way to completely sidestep that entire computational mess.
Okay, let's kick things off with round one, structure and relationships. Now, how does the actual shape of your data dictate where it should live? Take a look at this. Notice how one-to-many relationships naturally form a tree structure that branches out from a main root node. Think of something like a user profile or a resume on LinkedIn. One user has many past jobs, many degrees, and multiple contact methods, right? In database terms, these are one-to-many, or really one-to-few, relationships. And this is where the document model is absolutely fantastic. It excels at natively representing this tree-like structure. Because formats like JSON let you use nested arrays and embedded key-value pairs, you can store that entire resume, jobs, education, everything, right inside a single JSON document. When your code requests that user, the database just hands back a fully formed hierarchical object that perfectly matches what your application expects. There's no mapping phase, no complex translation. That impedance mismatch we talked about, it's completely gone, because the database structure and the code structure are essentially identical. But think about what happens mechanically if you try to force that beautifully self-contained resume tree into a traditional relational database. You have to use a normalization technique called shredding, and it is exactly what it sounds like. You are literally ripping that single document structure into multiple isolated tables. You need a base table for the user, a separate one for their jobs, a third for education, a fourth for contact info, and then meticulously link them all back together with foreign keys. We've all been there, right? Staring down a terrifying 5-table inner join just to render a basic profile page. For tree-structured data that you almost always load at once, shredding just leads to a totally cumbersome schema. It forces the database engine to work super hard, stitching disparate rows back together, burning memory and CPU, just to reconstruct something a document database could have handed you in a fraction of the time. However, the second we introduce many-to-many relationships, this clean tree structure turns into a tangled web. Let's say we want to standardize the organizations a person worked for, rather than just letting users type in plain text strings with typos. Now, many different people can work for the same organization, and obviously one organization has many employees. In a document model, one-to-many trees are easy, but many-to-many, that gets exceptionally messy. You can't just nest everything anymore without causing massive data duplication. So you're forced to start storing ID references to other separate documents. And to query those relationships, you essentially have to do manual joins right in your application code. You fetch the user document, grab the organization ID, and then make a whole second network trip to the database to get the organization data. Some developers will try to denormalize the data by duplicating the organization name inside every user's document, but that introduces a huge risk. If that organization changes its name, you now have to hunt down and update thousands of individual documents. If even one write fails, your data is out of sync. When you put these models head-to-head for complex interconnected data, the relational model absolutely dominates. The relational paradigm handles many-to-one and many-to-many relationships without breaking a sweat. It uses associative tables, which we usually call join tables. You just drop a discrete table right in the middle to link a user ID to an organization ID. And instead of forcing your application code to handle network round trips, you lean on the database's highly optimized internal query engine. Think about it. Relational databases have spent decades perfecting advanced math, stuff like hash joins, nested loop joins, and B-tree index lookups, to join data together with blistering speed. The query optimizer actually calculates the single most efficient path to get your data before it even runs the search. If your data looks like a highly interconnected web, say a social network or a complex financial ledger, the relational model's native support for joins makes it vastly superior. Moving right along to round 2, the schema debate. All right, let's unpack data flexibility. This is where you usually see the most intense religious arguments between backend devs. You'll constantly hear people confidently say document databases are schema-less, making it sound like you can just throw any chaotic data in there with zero rules. But I really want to shatter that misconception right now. Listen to this quote straight from the source material. Document databases are sometimes called schema-less, but that's misleading. There is an implicit schema, but it is not enforced by the database. Really think about what that means. Even if the database storage engine itself lets you write whatever bytes you want to the disk, the application code that eventually reads it absolutely assumes a specific structure. If your rendering code is expecting an integer called user_age to do some math, and that field is suddenly missing or written as a text string, your app is going to crash. The schema is always there. It's just been shifted out of the database and hidden inside your application logic. So to talk about this accurately, we have to define the difference as schema-on-read versus schema-on-write. Schema-on-read is your document database approach. The structure is totally implicit. The database just blindly accepts the data, and the structure is only interpreted later on the fly when the app actually reads it. This is great because you can iterate fast and add new fields without running tedious migration scripts. On the flip side, schema-on-write is the traditional relational approach. The schema is explicit, documented, and very rigid. Here, the database acts like an incredibly strict bouncer at the club door. It evaluates every single insert or update, ensuring that incoming data completely conforms to the rules before a single byte is ever written to the disk. A really good way for developers to think about this is comparing schema-on-read to dynamic type checking at runtime and schema-on-write to static type checking at compile time. Just like the fierce debates over dynamic Python versus statically typed Java, there's no absolute winner here. It entirely depends on your tolerance for risk versus your need for speed. Schema-on-read gives you incredible flexibility. It's a lifesaver if your data is super heterogeneous. Imagine you're building an IoT platform tracking telemetry from 50 different sensors made by 10 different companies. Every incoming payload is going to have wildly different fields and nested structures. You definitely do not want to run a blocking alter table command every time a new sensor comes online. That's where a document model shines. But if you're dealing with crucial records like financial transactions, where every single row absolutely must have an exact identical structure with no missing fields, the schema-on-write approach of a relational database is literally unparalleled for enforcing integrity and keeping your system clean. All right, let's jump into our final comparative round. Round 3, data locality performance. We have to weigh the physical storage implications here, specifically how these databases interact with the underlying hardware. One of the huge advantages of the document model is this concept of storage locality. Document models usually store all the data for a given record as a single, continuous string, often encoded in binary formats like BSON. Fetching an entire document at once gives you a massive performance boost at the hardware level. To get why, you just look at disk mechanics. Even with incredibly fast modern NVMe solid-state drives, sequential reads, which means reading data that's packed tightly together in one physical spot, are vastly faster than random reads. So when your app needs that user's profile, a document database just executes a single sequential read, pulling that continuous BSON string straight into the CPU cache in one rapid swoop. Relational databases really suffer here. Because the data was shredded across 5 different tables, the engine has to execute multiple random disk seeks, jumping all over the SSD to find those shredded pieces, load them into memory, and do expensive joins to glue them back together. But listen, that locality is a vicious, double-edged sword when it comes to write operations. The pro is obvious: rapid sequential reads if you need the whole document. But the cons are severe if your access patterns are highly targeted. It is immensely wasteful if you only need a tiny fraction of the info. The document database typically has to load an entire, massive, megabyte-sized document from disk into memory just to read a single Boolean field. And updates are even worse. If you want to change one minor thing, like incrementing a views counter, the database can't just update a single byte. It usually has to entirely rewrite that massive document back to the disk. And if your new value is bigger than the old one, causing the file size to grow, the database might have to physically pick up the entire document, move it to a completely new location on the disk, and update all the associated indexes. This creates massive write amplification. That's exactly why the standard advice for document databases is to keep your documents strictly bounded in size and aggressively avoid architectures that rely on frequent small updates.
Time to wrap this up. The summary. The great convergence.
So after all these years of debating which model is structurally better, there is a fascinating twist unfolding right now. These two supposedly opposite models are actually converging. The rigid relational databases have really softened up. Today, robust engines like Postgres and MySQL natively support highly optimized JSON columns. Like Postgres' amazing JSON B-type. You can store, index, and query flexible tree-like documents right alongside your strict relational tables. At the same time, the document databases woke up and realized that complex, many-to-many relationships are just an unavoidable reality of mature software, so they've been actively bolting on relational features. Document databases like MongoDB now offer powerful aggregation pipelines that can do server-side joins, and they've added robust secondary indexing so you can search interconnected data way more effectively. They're basically racing to meet in the middle.
What this convergence practically means for us is that relational document hybrid architectures are an incredibly powerful tool. You don't have to make this agonizing binary choice at the start of a project and just live with the unmitigated downsides of one side for the next 10 years. Instead, you can pragmatically mix paradigms in the exact same system. You can set up strict schema-on-write relational tables for your highly interconnected core transactional data, like billing ledgers and user-auth, where integrity is everything. But simultaneously, you can use native JSON columns in those exact same databases for your flexible schema-on-read data, like user dashboard settings or weird sensor payloads where you really need that development speed. It empowers you to literally harness the best of both worlds without deploying a bunch of separate infrastructure. I want to end on a question for you to take back to your next architecture review. Based on these specific engineering trade-offs, really evaluating the inherent shape of your data, your tolerance for schema enforcement versus flexibility, and your specific read-to-write ratio, which data model does your current project truly need? Take a step back and objectively audit your system using this framework. Look right past the marketing hype, analyze the real cost of your impedance mismatches, and go build systems that actually work harmoniously with the natural structure of your data. Thanks for joining me on this explainer, and I'll catch you next time as we keep breaking down the foundational concepts in system design.